Hi, today's lesson is going to be motion and force. So here are some pictures that we're going to be talking about that have to do with motion and force. The top left is talking about different types of forces. The top right is talking about speed, velocity, and acceleration. The bottom left is the laws of motion by Newton, Isaac Newton, and then on the right is talking more about gravity and friction. Our essential question is, how is the motion of an object affected by forces that act on it? Our science standards have not changed through the year. And our substandards for this lesson are going to be apply Newton's third law to design a solution to a problem involving the motion of two colliding objects, plan an investigation to provide evidence that the change in an object's motion depends on the sum of the forces on the object and the mass of the object, construct and present arguments using evidence to support the claim that gravitational interactions are attractive and depend on the masses of interacting objects. And finally, develop a model to describe that when the arrangement of objects interacting at a distance changes, different amounts of potential energy are stored in the system. We'll be talking about some of those in today's video. Just want to show you the objectives. There are quite a few. Let me just come back on for a minute. This is a longer video, so if you want to watch half of it now and then half of it later, that's strongly encouraged. And there are quite a few questions on this one, so plan accordingly as far as how long it's going to take you to get them finished. Okay. So here are some objectives. We'll talk about those at the end when we read the questions. More objectives, and more objectives. Notice that the objectives are all in order. So the questions will be in order on the slides. Use the slides. All the answers are there. Okay, how do you decide whether something is moving? Well, if you're riding in a car down the highway with your dog, to you the dog appears to be staying in one position. Well, you know that the dog really is moving, especially if he has his head out the window and the wind's blowing and his ears are flapping back, right? So what determines whether the dog is moving or not? Is the dog really moving? So there's your dog with his head out the window, smelling the air. An object is in motion if its position changes when compared to another object. Okay, think about that. An object is in motion if its position changes when compared to another object. So you need a reference point. A reference point is a place or object used for comparing to determine whether something is in motion. So objects that are fixed to the earth, such as a tree or a building, make good reference points. So in this picture of the dog, the tree would make a good reference point. That is not moving. That is stationed and stuck in the ground. So you can tell if the dog goes past the tree that the dog really is moving, even though when he's sitting next to you, he doesn't appear to be moving because you are moving along with him. So just like I said, if the tree is a reference point, the dog appears to move. If you, however, are the reference point, then the dog's position does not change. So what does that mean about motion? Well, that means that motion is relative, right? Why is motion relative? Well, because motion is determined by a reference point, and your reference point can change, right? So if you're comparing the dog to the tree, he's moving. If you're comparing the dog to yourself, he's not moving. So if you're sitting on a towel at the beach and use your towel as the reference point, you and the towel are not moving. But if you look up at the sky and you look at the sun and use that as your reference point, you're going to notice that the sun is going to be in a different position not too long after you look at it, right? Because you are moving quite rapidly because you are on the earth, and the earth is revolving around the sun. So the earth is moving. Relative to the earth, you are not moving, but relative to the sun, you are moving quite rapidly. So that's why motion is relative. Do you know how this ride shows relative motion? Okay, how would that ride show relative motion? It's a roller coaster, right? Yeah. Well, in motion relative to the track is stationary, right? It's in motion relative to a person, Get my spotlight here. A person standing on the ground, and it's in motion relative to the sun. It is stationary relative to another person sitting on the ride next to you, right? It's stationary relative to the seat, and it's stationary relative to the actual car that you're sitting in. How do forces affect motion? Well, lots of different ways. So the motion of an object can change when one or more forces act on the object. So a force is defined as a push or a pull. When one object pushes or pulls another object, the first object exerts a force on the second object. If you're pulling a wagon, you're exerting a force on that wagon. So here is a person pushing a car. Here is somebody pulling a wagon. Those are forces. They're exerting a force on the object, on the car and on the wagon. A force is described by its strength, how much of a force it is, and by its direction. Which way is the force going? Force strength is measured in newtons. So we're going to talk about newtons in a little bit. Named after Sir Isaac Newton, the man who discovered all these laws about motion and force. What are the types of forces? Well, there's contact forces and non-contact forces. What do I mean by that? Well, force is applied only when one object actually touches another is a contact force. When the little boy put his hands on the car and pushed it, that was a force by him touching it. Friction force is a contact force that two surfaces exert on each other when they rub against each other. Air resistance force is the force that is caused by air and is in the opposite direction to the moving object passing through the air. You can feel air force when you stick your hand out of a moving car. You'll feel that the wind, the air is pushing back, making your hand want to go backwards. You can feel the force. And then there's applied force. That is a force that is applied to an object by a person or another object. So that's the one I talked about where the boy was pushing the car. That's an applied force. Then you have non-contact forces. These are forces applied to an object, whether it touches the object or not. So what on earth do I mean by that? Well, gravity is a force, but it's non-contact. It pulls objects towards each other as a result of their masses. Magnetic force is non-contact, and attractive and repulsive force between electrically charged particles that are moving. And then you have electrical force. That's an attractive and repulsive force between electrically charged particles that are moving or stationary. So the difference between magnetic force is they have to be moving charged particles, and electrical force can be moving or stationary charged particles. That's the difference, very slight difference. So here are some examples of contact and non-contact forces. So here's your air resistance, the guy jumping out of the airplane, a parachuter. Here's the applied force, the boy's turning something with his hand. Here's the friction force, the girl goes down the slide, but she goes slower because her pants are rubbing against the slide. Then you have electrostatic force or electrical force, gravitational force, and then magnetic force towards the North Pole. What happens when more than one force acts on an object? So let's think about that a little bit. You have two types of forces, balanced forces, and that should say unbalanced forces. Let me fix that. Okay, let's fix that. So balanced forces and unbalanced forces. So balanced forces are when two forces acting on an object are equal in strength and opposite in direction. So a book on a shelf has two forces acting on it. It has the downward force of gravity, right, pulling it towards the earth, and that's equal to the strength and opposite in direction to the upward force of the shelf holding the books there. If the shelf were not a force, then the books would just fall through the shelf. So here's an example at the bottom there. You have balanced and unbalanced forces. So these here, they're balanced. One is pushing one way, one's pushing the other way. Here, they're both pulling the opposite direction. And unbalanced forces are when two forces acting on an object are not equal in strength and or not opposite in direction. So here's somebody pulling a book off the shelf. When they pull the book off the shelf, the pull of the person removing the book and the friction between the shelf and the book act in opposite directions. But the forces are not equal in strength and the pull is stronger, and so the book comes off the shelf. If they were equal and the friction was equal to the pull that the lady's doing with her hand, then there would be no way to get that book off the shelf. It would not move. Here's a picture of unbalanced forces. You have two people pulling and one person pulling. The two people are stronger than the one person. The force is unbalanced, and who's going to win the tug of war? Probably the two people. What is net force? The net force of an object is the combination of all of the forces acting on that object. So if the forces act in the same direction, you add each force, and the net force is the sum of all the forces. So here you see a 40 Newton force and then another person pushing it at a 30 Newton force. The amount of force being put onto that box is 40 plus 30, or 70 Newtons. If the forces act in opposite directions, subtract the forces, and the net force is the difference in the strengths of those forces. Somebody pushing from this way at 40, somebody pushing the other way at 30 Newtons. So it's 40 minus 30, so the force on the box is 10 Newtons. If net force equals 0, then the forces are balanced. So if this one was a 40 Newton push and this is a 40 Newton push, then the forces are balanced and the net force would be 0. If net force is not equal to 0, then the forces are not balanced. How do you calculate speed? First, we have to know what it is. So speed is the distance the object moves per unit of time. So speed is a rate. A rate tells you the changes in something for every unit of time. So the formula for calculating speed is speed equals distance divided by time. Distance divided by time. Divide the distance an object travels by the amount of time it takes to get there. So any unit that expresses distance over time is speed. You might have it in miles per hour, kilometers per hour, feet per minute, centimeters per second, meters per second, inches per hour, all kinds of ways. As long as you have a distance and you have a time, it's speed. The SI unit, or the standard unit for speed, is going to be meters per second, and it's written as meters m/s, meters per second. So let's talk a little more about calculating speed. Speed is the distance the object moves per unit of time. We learned that, and there's the formula. If a sled travels 5 meters per second at the top of a hill, this means that the sled travels a distance of 5 meters in 1 second. If the sled travels 15 meters per second at the bottom of the hill, because speed increases as you go down the hill, this means that the sled travels a distance of 15 meters in 1 second. So the greater the number of meters per second, the faster the speed at which the object is traveling. And that makes sense. If you can go more distance in the same amount of time, you must be traveling faster. What's the difference between instantaneous and average speed? Well, instantaneous speed, that's the speed at a particular instant in time. So for example, your mom may be driving 85 miles per hour on the highway, but then sees a police car ahead, and instantaneously her speed drops to 55 miles per hour. That's an instantaneous difference in speed, right? Average speed, however, is the speed over a certain amount of time. So your mom drove 10 miles to get to the highway, then 75 miles on the highway, and then once she was off the highway, she drove another 15 miles to reach your Chicago relatives. If it took her 1.5 hours to get there, these total miles, you can calculate her average speed for the whole trip. How do you do that? Well, you add up all the miles she drove, divided by the time it took her. So she drove 10 miles plus 75 miles plus 15 miles divided by taking her 1.5 hours. So that would be 100 divided by 1.5. If you did that, you would get about 66 miles per hour. That was her average speed on the trip. Using linear graphs to show speed. A distance versus time graph is a linear graph, and you should be very familiar with linear graphs. Oops, by now. So on this graph, the speed can be found by finding the slope of the line. The slope is the unit rate calculated by, and we have different ways to calculate it. Getting my spotlight. The change in y, distance, divided by the change in x, time. y2 minus y1 over x2 minus x1 if you pick 2 points on the line, or simply rise over run. So speed is really just the slope between distance and time, and you're very familiar with slope. How do you calculate velocity? Well, what is that? Well, velocity is the speed at which an object travels in a given direction. So velocity has everything to do with direction. You must know the object's speed in order to determine velocity. So here's a thunderstorm. Let's say you're at a picnic and you're told that the thunderstorm is traveling at 25 kilometers per hour. Should you prepare for the storm? Well, if you don't know the velocity or the direction of the storm, you don't even know if the storm is going to move in your direction towards you. So you have to know the velocity. That will help you make a decision whether or not to prepare for a storm at your picnic. Air traffic controllers, they have to use velocity a lot because they have to describe it. They have to know that airplanes will change velocities a lot, and any error in calculation of either the speed of the airplane or the velocity, the direction the airplane is going, could result in a collision of two airplanes. So it's very important in air traffic controlling. What is acceleration? Acceleration is the rate at which velocity changes. Okay, what does that mean? Well, a change in velocity can involve a change in speed, a change in the direction something's going, or it could be both. So in science, when an object accelerates, it means any change in speed. So it could be an increase or a decrease. Sometimes you call that deceleration, but it's also known as negative acceleration. Or any change in direction is considered acceleration, or both a change in speed and direction is also considered acceleration. So even an object increasing or decreasing in speed is accelerating. So a dog who starts running to chase a squirrel is accelerating. They are increasing their speed. A car that comes to a stop at a red light is also accelerating. It's called decreasing speed, and it's negative acceleration. That might be a little different concept for you to think about. Even an object traveling at a constant speed is accelerating if it changes direction. So a car rounding a gentle curve in the road or changing lanes is accelerating. It may not be changing in speed, but it's changing in direction. Acceleration, remember, is the rate at which velocity changes. So a change in velocity can involve a change in speed, direction, or both. Here's a basketball player. Where is his acceleration the most? This is a decreasing speed here, because as it's going up, it's slowing down. This is an increasing speed coming back down for the hoop. Both the decreasing and the increasing speed are called acceleration. The arched path also shows acceleration because the ball is changing directions. So this is where the ball is moving the fastest, right after it leaves the man's hands. And this is where the ball is moving the slowest, right at the peak before it starts to fall down from gravity. How do you calculate acceleration? If an object is not changing direction, moving in a straight line, you can describe its acceleration as the rate at which the speed changes. So we're not talking about things that are changing direction right now. We're just talking about things moving in a straight line. So here's the formula. Acceleration is equal to the final speed of something minus its initial or beginning speed divided by the time. Okay, so let's take a look. Since speed is measured in meters per second, m/s, which we talked about, and time is measured in seconds, the SI unit for acceleration is going to be meters per second squared. Where the seconds squared come from? Well, there's an S in speed, and then there's S in time. So that's why there's two S's. When speed is increasing, acceleration will be a positive value. And when speed is decreasing, acceleration will be a negative value. That makes sense because if you go up here into the formula, if your final speed is less than your initial speed, you're going to have a negative number on the top. That's going to mean you have a decreasing acceleration. So let's do some acceleration calculation examples. So I'm putting the speed calculation formula up there. Speed is distance divided by time. And I'm putting the acceleration formula up there. Final speed minus initial speed divided by time. So an airplane is moving down a runway preparing for takeoff. So there it is at 0 seconds. It hasn't moved at all. It hasn't started. Time is just going to start. So its speed is at 0 meters per second. After 1 second, it's over here now. It has gone 8 meters per second. That's its speed. It's gone 8 meters in 1 second. At 2 seconds, it has gone another 8 meters per second, or 16 meters per second. And then if it goes 3 seconds, it's going 24 meters per second, or it's gone 24 meters. So notice that the airplane's speed increases by 8 meters per second every second of time. So that means acceleration at the takeoff is equal to, let's use our formula, 24 was its final speed, 0 was its initial speed, and time was 3 seconds. So you divide that out and you get 24 divided by 3, which is 8 meters per second squared. Notice the second squared because acceleration has two S's, right? It has seconds and then it has the seconds in the meters per second. All right, so that's where we get meters per second squared. Let's see some more examples. Here's our formulas again for speed and acceleration. On landing, the plane touches the runway with a speed of 65 meters per second. Here it is landing now. And then after one, so it's going 65 meters per second. And then after 1 second, it has gone, the speed has gone down to 60 meters per second. So we'll notice the airplane's speed decreases by 5 meters per second every second of time. So the acceleration at landing is equal to 60 is the final speed minus 65, the initial speed, divided by 1 second of time. 60 minus 65, this is where we get our negative acceleration, negative 5 meters per second squared. Hopefully you understand these formulas and you'll be able to work with them. Acceleration is negative because the plane's acceleration is decreasing. Okay, let's look at a graph to show acceleration. So there's an accelerating graph. Grab my spotlight again here. Where'd it go? I'm looking for it. Here it is. So here it is increasing, and here's the acceleration decreasing over time. So as time increases, acceleration increases. As time increases, deceleration increase, or acceleration, it decreases. You could say it that way too. So notice that acceleration is not a linear graph. Why? Because acceleration is not constant. It usually changes. So here's a biker on a hill. Notice that a biker going downhill will have an increasing acceleration the farther down the hill he travels. His bike speed is going to get faster and faster and faster until he gets to the bottom, right? And also notice that this means he will travel farther per second near the bottom of the hill than at the top of the hill. So here's his distance when he starts out. Then for the same amount of time, there's his distance. And then for the same amount of time, as he reaches near the bottom of the hill, his distance he even goes farther. So his speed is increasing. What is Newton's first law of motion? There's Newton in the right-hand corner there. So a hockey puck won't just start moving if it is sitting still, and it also won't stop if it is moving while in the middle of the ice. That just wouldn't make sense. If you just all of a sudden saw a hockey puck sitting there by itself start moving, you'd kind of be freaked out by that, right? Or if you suddenly saw a hockey stick stop with nothing that stopped it, it just stopped in the middle of the ice. That wouldn't happen either. Why? This is because a net force must act upon an object to cause a change in motion. This natural reality demonstrates Newton's first law. So Newton's first law says an object at rest will remain at rest unless acted upon by a non-zero net, and then force should be highlighted as well. So you're going to have to memorize these three laws. An object at rest will remain at rest. It doesn't want to move unless something pushes it. And an object that's already, part B, object that's already in motion at a constant velocity will continue moving at a constant velocity unless acted upon by a non-zero net force. That means things want to go the same direction at the same speed unless something changes its direction or it hits something and it stops. A hockey puck sitting still will remain at rest unless a player hits it or applies a net force to it, right? And the puck will keep moving at a constant velocity unless the player hits it in a different direction, applies a net force, or the puck hits the wall and stops moving. Or eventually, because the puck is on Earth, it will stop because of friction and gravity pulling down on it. However, if that puck was in space and the hockey player hit it, it would continue forever and ever at that constant velocity because there would be no gravity and no friction to stop it. So let's learn more about Newton's first law, which is also called the law of inertia. So if an object is not moving, it will not start moving until a net force acts on it. If an object is moving, it will continue at a constant velocity until a net force acts to change its speed or its direction. If there is a net force acting on an object, it will accelerate. So this is called the law of inertia, Newton's first law. What is inertia? That is a resistance to change in motion. An object at rest is going to resist getting pushed to move forward. An object already in motion is going to resist a change to stopping it or a change to its changing its direction. So Newton's first law of inertia is demonstrated by you riding in a car. You are moving at the same speed as the car. When the car suddenly stops, in this case it hits a brick wall, your body wants to resist the change in motion. It wants to keep moving. Your body wants to keep going the way it's been going. That's inertia. So you keep moving forward at the same speed and direction you were going before the car suddenly stopped. A force such as the pull of a seatbelt is needed to pull you back from continuing forward. And that makes sense. That's the law of inertia, resistance to a change in motion. How are inertia and mass related? Which object is harder to stop, you or the car? We'll talk about the bottom in a minute. The car is harder to stop because it has more mass. The more mass an object has, the greater its inertia or resistance to change. If you look at the guy on the right there, he's putting a force, he's applying a force, the same amount of force to both the little girl and the guy. Notice how much more the girl is moving than the guy, because the guy has more inertia, more mass. So as mass increases in an object, inertia increases. Inertia is a resistance to movement. So as something is bigger and heavier, it resists moving. As mass goes down, inertia also goes down. The little girl is easier to push than the big guy. Look at these two guys, fat guy and skinny guy, really skinny guy. Who has more inertia? Resistance to moving. I hope you said the guy with more mass, the fat guy. Who will be harder to stop once they are already moving? If they were both flying through space and you had to stand there and stop them, who's going to be harder to stop? The fat guy. Who will require more force to get moving in the first place? Right, the fat guy. Okay, makes sense a little bit, I hope. Okay, what is Newton's second law of motion? We talked about the first one. Now we're going on to his second law. If you apply a constant net force on an object, how does changing the mass of the object affect its acceleration? So you're keeping the same force, the same push towards something, you're just changing the mass. How is that going to affect how much it accelerates? I bet you can tell me the answer, right? The fatter or the bigger the mass, the less it's going to accelerate. So assume the horse in this horse-drawn sleigh exerts a constant net force. If the sleigh is empty, it will accelerate quickly, right? If the sleigh is full, it will accelerate slowly. The acceleration of the sleigh will depend on the mass of the load it carries. So Newton's second law says the size and direction of a net force equals the mass times the acceleration. The net force will have the same direction as the acceleration. So there's a formula for Newton's second law. Net force is equal to mass times acceleration. How far it's going per second, or whatever the amount of time is you're using, and then the mass. So Newton's second law is called the law of acceleration. If the net force and mass are known, the acceleration can be derived by this formula. Acceleration is equal to the net force divided by the mass. So Newton's second law is also called the law of acceleration. This formula can be manipulated algebraically to solve for any one of the missing pieces. So if you were to, this is the original, acceleration is equal to force divided by mass. I didn't put NF for net force, I just put force. So acceleration is equal to force divided by mass. If you use algebra, you can move those around to get force is equal to acceleration times mass, or mass is equal to force divided by acceleration. You can use the triangle and cover up the thing you're looking for. So in a word problem, if you're missing the force, you cover up force and you see that A times M is your result. That's your formula. If you're looking for acceleration, you cover it up and then you have force divided by mass. Sorry about that. Apologize. Acceleration is measured in meters per second squared, and mass is measured in kilograms. Okay. So when you multiply mass times acceleration, then force is measured as kilograms times meters per second squared, or kilograms at the bottom here. Let me get my thingamabob. kilograms per meters per second squared. So this is the SI unit, okay, that you're going to use. So let's see how that works with newtons. So Newton is the SI unit for force. So 1 Newton is equal to 1 kilogram per meter per second squared. So 1 Newton is the force required to give 1 kilogram mass an acceleration of 1 meter per second squared. That's what a Newton means. It gives a 1 kilogram mass an acceleration of 1 meter per second squared. So let's see how we can use Newton's second law to do some calculations. So there's our 3 formulas, and if you prefer the triangle to memorizing the formula, feel free to use that. So a volleyball is hit and experiences a net force of 2 newtons, which causes it to accelerate at 8 meters per second squared. What is the mass of the volleyball? Okay, which formula am I going to use? I'm looking for the mass. I'm going to use that formula. Mass is equal to force divided by acceleration. Another way I could do it is cover up the m in my triangle, and I can see that it's F divided by A. So here, let's use the formula. Let's plug in the numbers. So the force is 2 newtons, and the acceleration is 8 meters per second squared. So now let's do the calculations. 2 divided by 8 is 0.25 kilograms. That is the mass of the volleyball. Okay, the same ball is hit again and experiences a net force of 3.5, and I think I forgot to put the rest in there. It would be an N. What is the acceleration of the volleyball? Which formula am I going to use to find acceleration? That one, or I can cover up the A in my triangle, and it's force divided by mass. So let's plug in our numbers. We have a 3.5 newtons of force, and we have a 0.25 kilograms of mass, and we divide them, and we get 14 meters per second squared. That's the acceleration of the volleyball. The same ball rolls horizontally along the sand and decelerates at a rate of 6 meters per second squared. Calculate the force of friction that caused the deceleration. Which formula am I going to use to find a force of friction? That one, right? Or I can cover up the F because I'm looking for force, and it's acceleration times mass. So we plug in the numbers. We have the rate of acceleration, 6 meters per second squared, times the mass. We have that. That'll give us the force of 1.5 newtons. So become familiar with how to solve these formulas under Newton's second law. Okay, now we're on Newton's third law of motion, and we're coming to the final stretch, guys. So gravity is pulling on each book in the downward direction. If the books did not push upward on each, if the shelf did not push upward on each book with equal force, the books would fall through the shelf. I'm going to fix that for you guys. Okay, I changed it. If the shelf did not push upward on each book with each equal force, the books would fall through the shelf. So the force exerted by the shelf is equal in strength and opposite in direction to the force the books exert on the shelf. So the shelf pushes upward on the books, and the books are pulled down by gravity, and they stay on the shelf. For all objects, so if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first object. So Newton's third law is, for every action, there is an equal in strength but opposite in direction reaction. We can do some examples of that. So it's called the law of action-reaction. An action force is always paired with a reaction force. Action reactions are all around you. How do I mean? Let's see. There's somebody on their skateboard. The action force is your foot pushing down on the ground. The reaction force is the ground pushing up on your foot. How about this gymnast? The action force is the gymnast pushing down on the balance beam. The reaction force is the balance beam pushing up on the gymnast. And a dog on a leash. The action force is the dog pulling on the leash. The reaction force is the leash pulling back on the dog. I told you they were all around you. So Newton's third law is called the law of action-reaction. More about Newton's third law. Some action reactions are easy to observe. So the skateboarder can feel the force of the ground on his foot. He knows his action, he knows the reaction. Some action reaction forces are not as easy to detect. So for example, when you drop your pen, the earth will pull the pen downward, but the pen also pulls the earth upward at an equal and opposite reaction force. But why doesn't the earth like smash into the pen then? Why doesn't that happen? Well, you see the pen fall, but you don't see the earth accelerate towards the pen. That is because Newton's second law says that if your force stays the same, but mass increases, the acceleration will decrease. So the earth is accelerating far less than the pen. Because Earth has such a huge, huge, huge mass compared to that tiny pen, its acceleration towards the pen is so very, 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 very small that you don't even notice it. All you notice is the pen dropping. Let's talk a little bit about balance and action-reaction forces. You have learned that two equal forces acting in opposite directions on an object balance each other and produce no change in motion, like the books on the shelf. So there is Newton's third law in action. There's an action and a reaction, okay? Why aren't the action-reaction forces in Newton's law of motion always balanced? Well, in order for forces to be balanced, we learned this in the previous slide here, they must act on the same object. Action-reaction forces are not balanced because they act on different objects. When a hockey player hits a puck, the action force is the force of the stick on the puck. The reaction force is the force of the puck on the stick. The puck has a much smaller mass than the player and his stick, so you see the puck accelerate, kind of like the earth pen example. Okay, let's talk about Newton's laws. Let's just put them all up there at once. So Newton's first law, an object at rest will remain at rest unless acted upon by a non-zero net force. And an object moving at a constant velocity will continue moving at a constant velocity unless acted upon by a non-zero force. Newton's second law, the size and direction of a net force equals the mass times the acceleration. The net force will have the same direction as the acceleration. And there's your formula, net force equals mass times acceleration. And 3, Newton's third law, for every action there is an equal in strength but opposite in direction reaction. Memorize these 3 laws. Let's see them in action. How do they work together? Here's a ride at an amusement park, maybe Six Flags, spinning swing. So Newton's first law, the law of inertia. When the ride starts, what does that say? Iberia pushes the rides back and there's, oh, inertia. That's supposed to say inertia. Okay, I fixed it. Okay, the first law of inertia. When the ride starts, inertia, am I still missing something? I'm missing the T. Pushes the riders back in their seats. They want to stay at rest. Newton's second law, the law of accelerations. As the riders accelerate from rest to reach the same speed, riders with greater mass will experience greater force. And then Newton's third law, the law of action-reaction. The riders exert an action force on the safety bar. The bar exerts the same amount of force in the opposite direction on the riders. Okay, your homework is going to be to answer these questions. All of them are in order. All of the answers are on the slides. So explain how I can know an object is in motion based on the idea of a reference point. We talked about the tree being a good reference point compared to a person next to a dog, for example. We had another example of the towel and the sun and the beach. Explain why motion is relative. Define force and explain 2 ways it can be applied. Define contact forces and list 3 types. Define non-contact forces and list 3 types. Explain the difference between balanced and unbalanced forces and give 1 example of each. Explain what net force is and how to calculate it. Remember, if you add them going in the same direction of the push, you add the forces together. If they are going in opposite directions, you subtract them. Define speed and write the formula used to calculate it right on the slides. List the difference between instantaneous speed and average speed and explain how to calculate average speed. There's a formula right on the slide there. Explain if a speed graph is linear or nonlinear and why. Define velocity. List the 3 ways to a change in velocity occurs. Define acceleration and list the formula for calculating acceleration. Explain if an acceleration graph is linear or nonlinear and why. List Newton's first law and give an example of this law in action. Define inertia and explain the relationship between mass and inertia. Remember, greater mass, greater inertia, resistance to change. List Newton's second law and give an example of this law in action. List the acceleration formula used in Newton's second law. List Newton's third law and give an example of this law in action. Explain why some forces are not balanced. Explain how each of Newton's 3 laws of motion work together on an amusement ride. You don't have to pick the swings, you can, but you could pick a roller coaster or some other ride if you would like. So that is the end. I know this was a little bit longer, but these were all necessary things for you to learn. So I will see you next lesson. Bye.